Okay, now let's take a look at example number 3. This example deals with friction calculation. We use Fanning friction factor here. And in next week's lecture, we're going to talk about energy balance and the pumping operation, in which we're going to introduce different friction terms. For this particular example, it's a simplified case of the flow problem associated with pumping that we're going to be covering next week. So here we have a tank, a overhead tank that is connected to somewhere through a piping system. The piping system has a length of 40 meters, and since it's an overhead tank, that means the driving force is produced by the height difference, delta H. Because we have this height difference from the tank to the exit of the liquid through the pipe, we're going to generate a pressure difference from this point to this point. And that pressure difference is determined by gravity. So rho g times delta H will give us the pressure difference that is going to be created. And the question is to answer, what is this height difference that we need to maintain if we want to get a 0.5 liter per second flow rate out of this pipe at the end? From the volumetric flow rate, 0.5 liters per second, the first thing to do is to calculate the average velocity of the flow. Right? The average velocity always is determined by the flow rate divided by cross-section area. So we need to calculate the cross-section area of the pipe, which we know has a 2 centimeter diameter internally. So we calculate A first. That is the result. Then again here, you always want to convert everything into SI unit. The base unit in SI unit system for length is meter, for volume is cubic meter. So 1 liter is a thousandth of a cubic meter. So after we do that, we can calculate the average velocity. That's 1.6 meters per second. Then with that, we need to calculate our Reynolds number, which will tell us whether we have a laminar flow or a turbulence. So we calculate our Reynolds number. This is our results. It's close to 23,000, which is certainly much larger than 2100 that we need for turbulence. So we're dealing with turbulence. And for turbulence, remember, for if we have a laminar flow here, for Newtonian material, for a Fanning friction factor, we can calculate the friction factor directly using 16 over Reynolds number. That's for a laminar flow. For turbulence, we cannot use that equation, but we can use Moody's diagram. And in a lecture note, you'll see that there's a link to a Moody's calculator. So basically, you don't need to go to a diagram to find the results from a graph, but you can pump in the numbers. Reynolds number is 22,933. And the roughness factor, and in this case, it's the relative roughness factor will be epsilon over D. That's 0.001. And you have these two values put into the Moody's calculator. Our factor, the Fanning friction factor, equals to 0.027. Once we know F, we go back to the definition of Fanning friction factor. This equation, remember, comes from the definition of Fanning friction factor, which is the shear stress at the wall, which is the kinetic energy density. By a rearrange a few terms, we can associate delta P to Fanning friction factor and the average velocity. And here we utilize the fact that we have a force balance. Again, let me emphasize this one more time. When we have a fully developed flow in a pipe, velocity, although is dependent on the location, but it's not dependent on time, which means there's no acceleration, which means the net force acting on each of the flow element is zero. Then your driving force caused by pressure difference has to equal to the resistance force, which is the shear stress. So that's how we can always figure out what the stress, the pressure drop is, because it's balanced off by the shear stress at the wall. And we calculate delta P, that is 237,772 Pascal. And as we discussed here, the pressure difference here is purely generated by the gravity acting on the liquid, because we maintain a height difference, so that we can figure out what that height difference is. So delta H is 28.2 meters. So that's how high that we need to maintain the tank. Obviously, you can see that 28 meters is very tall, and if you wanted to generate a flow rate purely by gravity, then it's a lot of times not realistic, which means we'll need to generate this delta P by means other than gravity alone, and that is we need to use a pump. So we're going to talk about pumping next week, and also here in this discussion, the fanning fraction factor accounts for the fraction due to the shear stress mainly happen at the wall. But there are other factors that's going to be contributing to the overall resistance. For example, in this case, 40-meter long pipe, 28.2 is the height difference. That means you will have to have this elbow here to change the flow direction, right? And such an elbow will be generating some resistance against flow as well. And when material flows into a pipe, flows out of a pipe, we call that sudden expansion or sudden contraction. Those are going to be generating resistance that you need to take into account as well. So for this simple example, we have not taken into account those factors. Well, next week when we talk about pumping, we're going to take into account those factors and say if we need to take everything into account, how do we quantitatively account for energy associated with these more losses, and we can have a more general calculation on pumping operations. And that's we're going to cover next week. For now, certainly what you need to take home with this example is the definition, the meaning of fanning friction factor. How do we find fanning friction factor if we know Reynolds number, and the roughness factor for the pipe system, and we'll go from there.